Okay, so today we're going to be talking about the last section on how to factor and solve polynomial functions. Today we're going to be looking at complex zeros, something we haven't looked at before in this class, but you have looked at before in Algebra 2. So let's remember a couple of things, starting with the fundamental theorem of algebra. Basically, it says a polynomial function with degree n has n complex zeros. Because remember, complex zeros are both real and non-real. Okay, remember the complex numbers are the biggest group of numbers that we have. Underneath the complex, we have real, we have imaginary. Together, they form the complex. And then under real, we have all the other kinds we know about. Now, linearization factor theorem. So if we have degree 3, if we have a degree 3, then we have 3 solutions, basically is what it's saying. Or if we have degree 5, it's 5 solutions. Degree 1, there's 1 solution. Okay, whether it's real or imaginary. Linear factorization theorem says that if a polynomial has a function of degree greater than 0, then it has precisely n linear factors. And remember, each of those linear factors represents a solution. So it's same as number of solutions from the fundamental theorem of algebra. So these linear factors and these zeros actually are a sum of the real and the imaginary. So n is going to equal the number of real plus the number of imaginary roots. Okay? Together, those end up being n, which is the degree. So what's the connection here? The fundamental polynomial connections in the complex case. What do we know? The following statements about a polynomial function f are equivalent if k is a complex number. All right, then if x equals k is a solution, and we know a solution is a root, right? Then f of x has to equal 0. In other words, when we plug it in, if it's a solution, it's a 0. We know k is a 0 of the function. Okay. In other words, zeros and solutions and roots are the same thing. All right. We also know that f of k must be equal to 0, right? And then if k is a 0, then x minus k must be a factor. Okay. Now, what do we know about imaginary numbers? The big thing we know about imaginary numbers is they come in pairs. You can never have one imaginary number, imaginary root. You have 2 of them. Okay. So let's look at what we've got going here. All right. So if we have a polynomial with rational coefficients, and irrational roots occur in conjugate pairs. Okay, so irrational roots occur in conjugate pairs, so that's irrational roots, and complex roots also happen in conjugate pairs. So we have pairs for irrational and for complex. So both of those have pairs. In other words, if a plus root b is a root, then a minus root b is also a root. This is a conjugate pair. If a plus bi is a 0, then a minus bi is also a 0. This is a conjugate pair. So you can see the roots make the irrational and the I makes them imaginary. So if we have one, then we already know we have the other. So if you can find one imaginary or conjugate root, then you know you have the other conjugate root. So in other words, it says find a cubic polynomial. We have root 2 and 5. Well, root 2 is irrational, isn't it? So if we have x equals root 2, then we also have x equals negative root 2. And then we have x equals 5. So leaving it in factored form, we know that f of x equals putting these in factored form, x minus root 2, x minus a negative root 2, which makes it x plus root 2, and then x equals 5 is x minus 5. So this accounts for this guy becomes that, this guy becomes that, and this guy becomes that guy. And we know that the solution is this. All right, now it says write it in standard form and identify the zeros of the functions and the intercepts from its graphs. Okay, well, let's start with the zeros first. Zeros, we know we're going to take x plus 2 and set it equal to 0, so x equals negative 2. We're going to take x minus I root 3, set it equal to 0, so x equals I root 3. And then we're going to take x plus I root 3, set it equal to 0, so we get x equals negative I root 3. So here are my zeros. Okay, now let's figure out what the standard form is. Standard form just says multiply it all together. So we're going to say f of x is equal to x plus 2, x minus I root 3, x plus I root 3, and I'm just going to FOIL these last two. So I'm going to FOIL this, and I'm going to say x times x. I'm going to save the x plus 2 to the very end, because it's easy. So x times x is x squared. Then we have this guy, which is plus x I root 3. We got this guy, which is minus x I root 3. And then finally we have this guy, which is minus I squared root 3 squared. Well, these two go away. So we're left with x plus 2 and x squared. Everybody remember that I squared is equal to negative 1. So this becomes minus negative 1, and root 3 squared, those go away, times 3. So this ends up being x plus 2 times x squared plus 3. Now we can finish multiplying it out. Multiply that out. FOILing again, we get x cubed plus 3x plus 2x squared, and then plus 6. So to clean this up, from highest degree to lowest degree, we know that f of x is equal to this. This is our standard form. Now, what that means is we can find our y-intercept, because we know our y-intercept is always just the constant. So our y-intercept is the 0.06, okay? And that's it for that. Now, find a polynomial given complex zeros. All right, so given a complex zero, what do we know? Well, we know we need to find the degree. So we know we have 1, 2, 3, but this guy comes in a complex conjugate pair. So then we also know we have 2 minus I, so this makes 4. So we have a degree of 4. Now all we have to do is put them into their factored form. So negative 3 becomes x plus 3. Negative 4 becomes x plus 4. This becomes x minus 2 plus I. And then we have x minus 2, minus I, conjugate pairs. So this is a conjugate pair. All right, so now all we have to do is multiply these guys together. Okay, so let's do that. So if we multiply these two together, we get x squared plus 4x plus 3x plus 12. And then we're going to do the same thing for this guy. We're going to do x squared minus 2x minus xi minus 2x plus 4 plus 2i. And then last but not least, plus ix minus 2i and minus I squared. All right, so we get minus ix plus 2i minus 2i. Those are always going to go away. And then the I squared is going to become, this becomes negative 1, doesn't it? So what do we end up with here? X squared plus 7x plus 12 And then we end up with x squared minus 2x is minus 4x plus 4, and this minus a negative becomes plus, so plus 5. Now, all we have to do is finish multiplying out. X squared times x squared is x to the 4th minus 4x cubed plus 5x squared, 7x squared minus 28, I'm sorry, 7x cubed, excuse me, minus 28x squared, and then plus 35x, and then last but not least, 12 times x squared is plus 12x squared minus 48x, and then plus 60. Cleaning this all up, we have x to the 4th minus 4x cubed plus 7x cubed is plus 3x cubed. 5x squared minus 28x squared plus 12x squared. So 5 minus 28 is negative 23 plus 12 is negative 11. So minus 11x squared. And then finally, 35x minus 48x makes negative 13x. And then plus 60 sits by itself. So this would be my answer. Okay. Let's do another one. Multiplicity of 2, what does that mean? That means that we have x minus 1, but we have x squared. This guy has a conjugate double, so we know it has a conjugate pair of 1 plus I. So we know the degree is going to be what? 1 here, 1 here, 2 here, so the degree is 4 again. So we should end up with x to the 4th at the beginning. So let's do this. So we end up with x minus 1 squared times x minus 1 plus I times x minus 1 minus I. And we're going to multiply this all the way out together. U to multiply it out, x plus 1 squared becomes x squared minus 2x plus 1, square double square. This guy is going to become x squared minus 2x plus 2 when you work it all the way out. So last but not least, we end up with x to the 4th minus 2x cubed plus x squared minus 2x cubed plus 4x squared minus 2x plus 2x cubed squared minus 4x plus 2. Clean it all up, we get x to the 4th, 4x cubed, 7x squared, 2. All right, so now how do we factor if we have complex zeros? This is going to piggyback on what we did last time. So we're going to do our p's and q's. So our p's come from 8, so that's plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Q's, thank goodness, are just plus or minus 1. So my p over q's are going to be plus or minus 1, 2, 4, and 8. All right, so now we got to find a couple that work. So let's see if what we know. Let's try our signs. So we have positive, negative, negative, positive, negative, positive. So we know we have 1, 2, 3, 4 sign changes. So we have 4 or 2 or 0 positives. Now we're going to go, this is going to change to negative, this is going to stay negative, this is going to change to positive, this is going to stay positive, this is going to go positive, positive. So we have one sign change, so we have one negative root. And then one negative real. So, one negative real means I'm going to start with the negatives. So I'm going to start with, and I only have so much room, so I'm going to pick the one I know works. So negative 2. So we have 1, negative 3, negative 5, 5, negative 6, 8. Bring this down. We have 1, negative 2, negative 5, positive 10, 5, negative 10, negative 5, positive 10, 4, negative 8, and that's 0. Boom. We've got 1. That's our negative. Now it's the only negative I know, so I don't have to try any of the other negatives. So now I'm going to try the positives. So I'm going to take 1 and put it into this and see if it works. Sure does. So I know 1 works, and now I'm going to try another one. I happen to know which one it is. Since I have a 2 and I'm going to end in an 8, it makes sense that I would also somewhere have to have a 4. So I'm going to try 4. Bring down 1, 4, 0, 0, 1, 4, 0. Yep. And this, guys, is x squared plus 1. So what I know right now is I have x plus 2. That comes from this guy. I have x minus 1, comes from this guy. X minus 4 comes from this guy. And then x squared plus 1. This is my factored form for f of x. Okay? Now, I have to solve this to find my other zeros. To solve my zeros, I'm going to take x squared plus 1 and set it equal to 0. That means I'm going to subtract 1 from both sides, so I end up with x squared equals negative 1. I'm going to take the square root of both sides. So x equals plus or minus the square root of negative 1, which is plus or minus I. So my roots, or zeros, are as follows. Negative 2, 1, 4, I, and negative I. And that is 5. And look at the degree right here, 5. Okay? That's how it works. All right, so now what do? We have 2x to the 4th. So what we're going to do is, this is where long division comes into play. They've given us 1 root right here. So if we have that, we also have its conjugate pair, minus 2i. So we are going to take x minus 2i, multiply it by x plus 2i, because I know both of those are roots, right? And I'm going to figure out what I have. And this is going to keep me from having to use p over q's, because quite frankly, this and this are going to make for a lot of p over q's. Huge number. You don't want to do that. So I'm going to end up with x squared plus 4 from this. This and this are going to go away, and this becomes minus 4i squared. That becomes negative 1, doesn't it? And so this would be minus 4i squared. Excuse me. Should have been minus. Which means this is x squared plus 4. Now, what I'm going to do is I'm going to take x squared plus 4, and I'm going to divide it into 2x to the 4th plus x cubed minus 7x squared plus 4x minus 60. Boom. So now I got to figure out 2x to the 4th. X squared goes in how many times? 2x squared, right? So this goes here. I'm going to multiply it by this. So I end up with 2x to the 4th plus 8x squared. Minus, that goes away. We bring down x cubed minus 15x squared, and then bring down 4x. Now we start all over again. I'm going to take x cubed, divided by x squared, we get x. So this is positive x. Multiply it in, we get x cubed plus 4x. That goes minus, that goes minus, that goes away, negative 15x squared. Bring down minus 60. And one last time, negative 15x squared. X squared, we get negative 15. So this is minus 15. Multiply it, and we get negative 15x squared minus 60. But if we change it, it becomes 0. So it does go in evenly. So what we know right now is that we have x minus 2i, x plus 2i, and then 2x squared plus x minus 15. Well, guys, that I can try to factor. I'm going to try to factor this. Crisscross it. We have negative 30 in the top, positive 1 here, which makes 6 and negative 5. So this becomes x plus 6 over 2, x minus 5 over 2. This reduces to x plus 3. This won't reduce, so we slide it to the front, 2x minus 5. So now we also have x plus 2i, x minus 2i. So what am I, so these are my factors. My zeros are 2i, negative 2i, negative 3, and positive 5 over 2. Bing! Now, finishing up here, it says factor over the real numbers. Irreducible quadratic factors, that means you don't have to find the complex numbers. So irreducible quadratic factors means don't find the complex roots. So if you have something that won't factor, just leave it. So P's for this guy are plus or minus 1, plus or minus 2. Q's are plus or minus 1, they're coming from this, and plus or minus 3. So P over Q's aren't very many. Plus or minus 1, plus or minus 2, plus or minus 1/3, and plus or minus 2/3. So I'm going to start with, let's see, positive, negative, so we've got 1, 2, 3 sign change, so 3 or 1, positive real. Changing signs, this becomes negative, this stays negative, this becomes negative, this stays negative, so we have 0 negative real. So get rid of all those, so we're just going to start with positives. So I'm going to start with positive 1, 3, negative 2, 1, negative 2. Bring it down, we get 3. We got lucky right off the bat. So what we know is my factored form is f of x so far is x minus 1, and then this is going to be 3x squared plus 1x plus 2. So let's try to factor that. 3 times 2 is 6. What multiplies to give us 6 adds up to 1? Nothing. Won't factor. So we leave it. So that's the final answer. All right. Last but not least, how do we sketch a graph with repeating zeros? Multiplicity of negative 3, multiplicity of 2, 4 has a multiplicity of 3, a is greater than 0. Okay, so let's look at this. This is a root of negative 3, so this becomes x plus 3. We know that this multiplicity is 2 means that. And then we've got 4, so x minus 4 with a multiplicity of 3, so this is up here. A being positive means the, we know this has a degree of 5 and a lead coefficient that is positive, so we know it has to end up doing this, don't we, somewhere along the way. This right here means it touches, it bounces, right? So this is a bounce, this is a cross. So how do we do this? Well, let's put this on here. We have a root at negative 3. We have a root at 4. We know the one at negative 3 bounces. It's coming from below. So if this thing is coming from below, it's going to come up here, bounce off. It's going to have to go back down. We don't know what it is. So let's figure out what f of 0 is. We need to know what the y-intercept is. So the y-intercept is going to be f of 0, right? So that's going to be 0 plus 3 squared, 0 minus 4 cubed. So that's going to be 9 times negative 64, which is equal to negative 576. So we're going to say this down here is negative 576, since I'm just literally figuring out what's going on. So this is going to have to go down and then come back up. This is cubed, so remember, we know it does that snaky thing. So it's going to come up here, snake across, and cross up here, and go up. And that's, guys, how we do it. This bounce, let's highlight the parts. This bounce at negative 3 is this. This cross at negative 4 is this, and because it's cubic, it kind of does the snaky thing. And then the last feature we had was the y-intercept at negative 576 is right here, and that helped us. Now, this stuff right here gave us our ends, which now also match. Last one. So how do we do this? We have a root at negative 1. We have a root at 3. Negative 1 and 3. This is a less than 0, which means it's negative. So 2 and 2, that's a degree of 4. This means it bounces. This also means it bounces. So if it is even degree and it's negative, we know eventually it has to do this, don't we? So we know what its end behavior is. So the last thing we need to do is figure out what its y-intercept is. So its y-intercept, we're going to have x plus 1 squared, x minus 3 squared, that comes from here and here, going into our factored forms. The squared is the multiplicity, so we're going to plug in 0. 0 plus 1 squared, 0 minus 3 squared, so this is 1 times 9, so it's at 9. Oh, but it's negative. A is negative, so we got to multiply this by a negative. So it's at negative 9. So down here at negative 9, we know we have our y-intercept. So how do we do this? Well, we know it starts downward, so it has to go down, has to come back, go through the y-intercept, touch here again, and now it's going back down. See the touch and the touch? So bounce and bounce, we're here and here, those bounced. The ends, here and here are the ends, and those match. Y-intercept is here. So we've got those. So that's how we do it. All right.